What is I to the power of I? This problem seems impossible. It's famously known as the imaginary paradox, and it asks a question that seems like a joke. Most people assume that if you take an imaginary number and raise it to an imaginary power, the result must be like the most imaginary thing ever. But they're wrong. And the result is actually a plain real number. We've been lied to about imaginary numbers. We're taught that I, the square root of -1, is this other type of number that lives on its own axis, forever separate from our real world. But if you take I and raise it to the power of I, the imaginary part does not get smaller. It's gone. Think about that. An imaginary base, an imaginary exponent. Yet the answer is a real number you can find out on a standard ruler. To solve this, we need to use one of the most fundamental formulas for mathematics, Euler's identity. So, how can we use Euler's identity to solve this problem? Well, to solve this, we need to rewrite I in its exponential form. Euler's identity tells us that e to the power of I theta equals to cosine theta plus I sine theta. If you want to just get I, we need the cosine part to be 0 and the sine part to be 1. That happens at an angle of 90 degrees or pi over 2 radians. So we can rewrite I as I is equal to e to the power of I pi over 2. This is the same number, just very different outfit. Now we take our original problem, I to the power of I, and substitute our new version of I into the base. And then we get e to the power of I pi over 2 to the power of I. According to the rules of exponents, when you raise a power to a power, you multiply them. So we multiply I pi over 2 by I. So basically this will equal to e to the power of I squared pi over 2. And we know that I is the square root of -1, so I squared is -1. So this will just equal to e to the power of -pi over 2. And we see that the I disappears entirely. There are no more imaginary units left. No I, no complexity. Just e raised to the power of -pi over 2. And if you punch that into a calculator, you get approximately 0.207. And that is how you solve this problem.